going to talk about the connection between cosmic ray, clouds, and climate. And I'm going to be slightly more a technical talk. I will do it as gently as possible, but start with the idea that you have a supernova that goes off, one of the main characters in what I'm going to talk about is cosmic rays, and cosmic rays are mainly produced when you have supernova, which are these big stars which are exploding, and they produce a shock front that accelerate particles to extremely high energy. And it means that the interstellar space is actually radioactive, and particles are moving through the interstellar space, and some of them, they enter into our solar system. And as we already heard, the solar activity can actually modulate how many cosmic rays that are entering into the inner part of the solar system. If we look at this figure, we have measurements from about 1950 until recently. And you see in the top figure, the blue figure, which is changes in cosmic rays, which are measured by what we call neutron monitors. And you can see this beautiful 11-year cycle where the intensity goes up and down. And below in the orange, you see the sunspot number. And you can see you have this inverse correlation. So when you have a high solar activity, the sun's magnetic field works as a better shield against cosmic rays, so fewer cosmic rays enters into the Earth system. So the cosmic rays, as they enter the solar system, some of them will end up in the top of the atmosphere. And what they do, they produce what we call a cascade down through the atmosphere. What you see here is, I think, it's a very high energy proton going into the atmosphere, and it's producing a lot of secondary particles. It is ionizing, as we already heard, the atmosphere. So most of the ions that we have in the atmosphere, in particular all the oceans, is almost exclusively from cosmic rays. In addition, we produce what we call cosmogenic isotopes, things like carbon-14. You know, carbon is also entering into the leaves of organic material in a tree, for instance, and by looking at how much carbon-14 there is, which is produced by cosmic rays, you can say something about how active the sun was at that year. And if you have tree rings and you have old trees, you can go back at least and even more than 10,000 years. And that's one of the ways that other isotopes are produced by cosmic rays, like beryllium-10. And beryllium-10 has a tendency to attach to aerosols in the atmosphere, and the aerosols then become snowflakes, and the snowflakes falls on, for instance, the ice sheets in Greenland. And then by looking at how much beryllium-10 you have in the ice sheets, you can say also something about how active the sun was back in time. And beryllium-10, you can go even further back in time than what you can do with the carbon-14. So the interesting thing about cosmic rays in the atmosphere is that each time there is a large change in the cosmic rays, there seems to be a change in climate. You have seen so many examples, the change in temperature over the last 1,000 years. You can see that you have a medieval warm period. For about 1,000 years, that's when the Vikings went to Greenland, and they stayed there. But around 1300, and the first settlements, they started to get into problems around the year 1500. The last settlements were gone. And that is because we entered into the Little Ice Age, so it was much harder. Came out of the Little Ice Age, which is quite fortunate because we are living in a much better time than what people were enduring during the Little Ice Age. If you look at the bottom figure, you see this correlation. This is from carbon-14 and beryllium-10. It is increasing downwards, so you have the opposite. So where it looks like it's low, it's actually because the cosmic rays are quite high. So when you have high cosmic rays, you have a cold climate. So that's the question that we asked actually now more than 20 years ago was, what could be the connection? I mean, why should there be a connection between solar activity and climate? And since the idea that solar irradiance probably not could explain what we were seeing, the idea was to look elsewhere, and the idea was to look at things like the Earth's cloud cover. What you see here important for the Earth's energy budget, the net effect is on the order of 20 to 30 watts per square meter. And that means that if time was to take satellite data and try to compare changes in Earth's cloudiness from satellites with changes in the cosmic rays. And this is the figure, the changes in cosmic rays measured by neutron monitors. So these are instrumental records of the cosmic ray flux of secondary particles that enters into the atmosphere. And the blue curve is low clouds from what the data set called the ESCIP data set. And you see this very nice correlation between the two. And that was, of course, that was an inspiration that there could be such a connection between cosmic rays and clouds. But it's not any guarantee that there is a real link. It could be just correlations by accident, of course. At that time, it was very uncertain, and there was no mechanism to explain what was going on. It could also be inspiration to do further work. Now, the changes that you see here are of the order it's on the order of 2% changes in the cloudiness of low clouds, and that is actually on the order of 1 watt per square meter over the solar cycle. And if I show the figure that Nir also showed, which is that the ocean heat content or the sea level surface temperature or what is the sea level change, all of these data, independent data, are all showing that the energy that goes in and out of the oceans over 11 years is on the order of 1 watt per square meter. And it fits very nicely with what the clouds are doing. And again, it's almost an order of magnitude larger than what you get from solar irradiance. And over this period here, the solar irradiance is measured by satellites. So the 11-year variations in solar irradiance is actually too small to explain what we're seeing. So there is an amplification mechanism going on. So the problem is, we have an empirical evidence that there is a relation between cosmic rays and clouds. But of course, if that is the link, the question is what would be the mechanism? And that's actually what we have been working on for more than 20 years. And the general idea is that we start from the left-hand side, where we have the ionization in the atmosphere from cosmic rays. And then the idea is that this ionization with the ions, they help stabilize gases in the atmosphere, so you get small stable aerosols. And this is what we call nucleation. So we get nucleation of particles. And then subsequently, they have to grow because they are 1 to 2 nanometers large, and then they have to grow maybe to 100 nanometer before they actually affect the clouds. And that means that they have to increase by almost a factor of 1 million in their mass. So the idea is that by changing the ionization, we change the number of what we call CCN, or this is also called the cloud condensation nuclei. And if we change the cloud condensation nuclei, the idea is then we change the properties of clouds. And I can show you that this is actually the case, because if we look at this picture here, where you see this satellite picture of the oceans, and you have a large region with low clouds, and you see all these stripes, and this is called ship tracks. So these are ships sailing along, and because they had this dirty fuel, they pump out extra aerosols. So you can see in the wake of the ships, these aerosols enter into the clouds, and they actually changes the microphysical properties of clouds, and you can see they're much wider. And if you could do a slightly larger version, and you can see that it is actually the individual clouds that are changed, and it's not just some kind of pollution directly that you are seeing. So we had this idea that there should be a connection between cosmic rays and the formation of aerosols. So we had what we can call an experimental challenge, because now we could formulate a theory that if we change the ionization, we should be able to see nucleation of small aerosols. And this was the first part of our work that was done between 2004 and 2007. And we had this experimental chamber. And the idea is that we put in some gases which are important, which is sulfur dioxide, it's ozone, and it's water vapor. That is actually fundamental ingredients also in the atmosphere. And the atmosphere we have in the chamber is very similar to what you have over the Pacific Oceans, for instance. And when you have these gases inside the chamber, then we have some lamps that can irradiate the chamber, which mimics the sun, and we get photochemistry, and we produce sulfuric acid. And sulfuric acid is one of the most important molecules for building and growing aerosols particles into cloud condensation nuclei. And it's produced completely naturally in the atmosphere, although sulfuric acid sounds really bad. It is in extremely small concentrations. So we had this concentration in the chamber. We kept everything constant except the ionization. And we got this result you can see here. So along the lower axis, the horizontal axis, we have the increase in the ionization that corresponds to the cosmic rays. And on the other axis, we have the number of small particles produced, that is small aerosols on the size of about 3 nanometers. And you see that as we increase the ionization, we increase the number of small aerosols. So there is a nucleation. It is that they actually have to grow quite a lot, as I already mentioned. Here you see the relative size between the small nucleated aerosol. It has to grow to a size that you can see here. And if this small aerosol does not grow to cloud condensation nuclei, there would be no effect on clouds from the cosmic rays. And the thing is that many things could go wrong before you end up to become such a large particle. We were very optimistic. However, they started doing numerical experiments. What you see here is all the numerical models, or the global circulation models, where they had very sophisticated aerosol models. They all had the result that the particles grew, but very, very few survived to cloud condensation nuclei. So that meant that from 2009 and onwards, it was quite clear that in the media and many scientists were saying that what we were doing was not, it was a good idea, but it's all wrong because it doesn't work. And it was sort of written everywhere that what we were doing wasn't working. So you can see here there were quite a lot going on. So that was the end of the theory. However, as our experiments and try to figure out what was going on, so the real problem is now not this part where we have the nucleation of the small particles. I mean, even the cloud is a chemistry that was going on, and the chemistry reactions and everything seems to be working fine. But in the experiments, we couldn't find that thing. So the theory starts all over again, and it turns out, hang on. So why can the particles grow to cloud condensation nuclei anyhow? So imagine that you have an aerosol here that needs to grow, and you have the ions here. So what is happening is that there is an interaction between the ions. So they actually stick to the aerosols, and when they stick to the aerosol, they actually add a little mass to the aerosol, a very small part of the mass. And it turns out that this type of interactions, there are 4 types that can be going on. It has to do with, is so far completely ignored in all modeling, and so it's not very strange that you will not see the effect in these global models, because these effects are not included in the models. So let me give you a few numbers. Now, when you have an aerosol, I told you that a lot of the growth is caused by sulfuric acid. So sulfuric acid sticks to the molecules or to the aerosols, and the aerosol grow by that way. Typically in the atmosphere, you have about 1 million of these aerosols, of the sulfuric acid molecules. But the number of ions is only on the order of 1,000 ions per cubic centimeter. So naively, if you just take these numbers, you will find that the growth from ions would only be about 0.1%, so it's completely negligible. And that's why people have probably ignored these effects. But it turns out that because these ions are charged, they actually, you have to take into account that there are Coulomb forces, there are mirror forces, and there are van der Waals forces that all help this interaction. So you can say you have enhanced interactions. And these enhanced interaction actually means that the growth rate, instead of being 0.1%, it is actually increased by almost 2 orders of magnitude, almost a factor of 100. And that means that in the atmosphere, 10% of the growth of these particles is actually caused by the ions. That is quite a lot. In our experiments, because we cannot have such a low concentration of sulfuric acid, because then things will grow so slowly that we will lose all our particles. So we have to have a fairly high or relatively high concentration of sulfuric acid, and the growth rate is only on the order of 1%. So here we have the theoretical foundation, but what we have to do is try to see if we can show it experimentally. And that's a real... So let me show you the sort of inspiration for the type of experiments that we are doing. This is actually aerosol formation in a forest in Finland. The concentrations of gases, because it is in a forest, is completely different from what you have over the oceans. But what you have here is the day as time goes along, and here you have the size. So this is 1 nanometer, this is 10 nanometer, and this is 100 nanometer. So here there are cloud condensation nuclei. But you see, as the sun goes up, you get the photochemistry, you get sufficient with sulfuric acid, so you can actually start the nucleation. So you have particles that the data seems to be folding right according to the lines, which is the theory. So it indicates that the theory and the experiments are fitting quite well. So let me just summarize the mechanism. The idea is that we have some gases in the atmosphere that are produced perfectly naturally, probably from photochemistry, but some of the species are actually from bio processes. And then you have the ionization from the Milky Way, where the sun can modulate how much gets into the atmosphere, so you get the nucleation. But the ions are not just helping the nucleation, they're also helping the growth. And by changing the number of cloud condensation nuclei, you are changing the properties of clouds, and then in the end, the energy budget of the Earth. So let me conclude this talk. We have cosmic rays that comes in, and they are producing ions in the atmosphere. This is not controversial at all. This is an experimental fact, observational fact. And also the ions, they help this nucleation formation of small clusters of small aerosols. These small aerosols have to grow. And then the second thing, which is the problem that we solved recently, is that the ions also helped the growth of these small particles to become cloud condensation nuclei. And that means that we sort of have the whole chain now secured both observationally, theoretically, and experimentally. So I think that part looks very good. We would like to do some more work also on the how it changes the radiative properties of clouds, and that will come soon. So the implications is that when you have more cosmic rays, you actually change the properties mainly of low clouds, and also because low clouds are the most important clouds for the Earth's energy budget. So when we have fewer cosmic rays, we actually get a warmer world, and maybe, 20th century warming might actually be because of changes in solar activity, and this mechanism that I'm of my talk. Thank you.